then they were split. That left the Aldol chapter a little weak, to be honest. So I kind of like put them back together so that we could get them done at once. And that'll give us a little more time to review towards the end of the semester. In this chapter, in this lecture, we're going to talk about carbonyl alpha substitution and condensation. It's all basically the same sort of reaction. We talked about enols for a very long time, actually. First time we met an enol was way back in hydration of an alkyne. If you remember, hydration of an alkyne generated something like this. We called it an enol, and we said that it converted spontaneously back to the carbonyl compound. Since then, we've talked about enolate anions. Enamines, actually, enamine anions, and we did enolate anions of carboxylic acids in chapter 20. So today we're going to explore this a little bit more. Now, way back in the day of alkynes, we said that this converted instantly back to the ketone. In fact, of course, it's an equilibrium. We start off with something like cyclohexanone. It will form the enol. The equilibrium constant for this, however, is such that 99.999% of the stuff is actually the ketone, with just a little tiny bit of the enol present. Nonetheless, it's there, and enough of it is there that we can use this in chemistry. If we look at enolization, we can describe this as an acid-base equilibrium. Here I'm going to use a base, pull off a proton, and make an enolate anion. This meets the definition of a simple Bronsted acid. We have a Bronsted base on this side, we go to BH, an acid, and we go to the enolate anion. Because of this, we can write an equilibrium. Equilibrium constant for the acid dissociation constant would be products over reactants. And for a typical sort of enolization, equilibrium constant is 10 to the minus 19. Of course, we know that that means the pKa for this ionization is about 19. Let's just refresh in our minds what pKa's are, because that goes way back to general chemistry. The smaller the pKa, the more this equilibrium lies to this side, and the stronger the acid. So small pKa, strong acid. Any questions? Now this is a very special type of acid. Here we're losing a proton from a carbon, and this is the concept of carbon acidity. The same basic rule applies to everything that we've talked about in terms of acidity. Basically, the more stable the anion, the stronger the acid. These are carbon acids. Starting down here with ethane. Ethane is a very, very, very weak acid, pKa of around 60 or so. This would form the ethane anion, a carbanion, which we all know is very, very unstable. Moving our way up, we get to things that have nice moderate pKa's. Look up here at pentane dione. Pentane dione has a pKa of about 9-ish. That's equivalent to phenol. It's a nice, decently strong acid, actually. Now, why do you suppose that pentane dione would be such a strong carbon acid? Well, to say my words back at me, that must mean it has a very stable anion, correct? If you think about the anion, the enolate anion that you form, it's actually resonance stabilized, isn't it? So our hybrid looks something like this. Resonance is our friend in organic chemistry, isn't it? More stable the anion, stronger the acid. Here we have a nice resonance stabilized anion, and it's very, very stable. You can also resonance stabilize this from malonitrile. That's why it's so low. And then as you add electron withdrawing groups, or take them off as we go down this way, the pKa's get higher and higher. Any question on just the concept? Well, let's look at this in an intuitive fashion then. Go ahead and look at this collection and decide to yourself which of these is going to be the strongest acid and which you would expect to be the weakest acid. In all cases, just think about your anion. Up here we would make the benzene anion. Now there's no way to resonance stabilize that, is there? We lose a hydrogen, we always have this vacant spot on the ring. That's going to be pretty unstable. If we made an anion here in the middle, it'd be next to two electronegative oxygens. That's better because they'll suck electrons away. Here we have a trifluoro group. That's really good at sucking electrons. That'll help stabilize that anion. We already know that ketones and aldehydes are around 19-ish for a pKa. And this guy, well, this guy looks a whole lot like our pentane dione, doesn't it? So we can make an anion here and resonance stabilize up on both carbonyls. The actual ordering is something like this. Benzene is down here about 60-ish, and this diester is up here at 13. Once again, the more stable the anion, the stronger the acid. Now we're going to talk about 5 or 6 basic types of reactions in this chapter. We're going to be making carbanions, mostly enolate anions, and then we're going to do things to them. An example, if we start off with methyl cyclopentanone, we could form in base an enolate anion here. We will see that this enolate anion can be used as a nucleophile. That is, we can attack an alkyl halide, or in this case, let's just attack bromine. If we dumped in bromine in the presence of this enolate anion, it would be alkylated at this point, and we would get the alpha-bromo compound. So that's one of the first things we're going to talk about, is simple alkylation or halogenation, alpha to a carbonyl. Remember, this is our alpha carbon, alpha beta. We'll also see a little bit later that once we have substitution at the alpha position, if it's a leaving group, the leaving groups will be halogens or OH, hydroxyl group. We can do an elimination. Elimination will give us an alpha beta unsaturated carbonyl compound. Now that's useful because we know lots of chemistry of alkenes here. We also know we can do Michael-style additions down here at the beta position and elaborate this into almost anything we want. So it's a very useful sequence. Alpha substitution and elimination. Let's think about the alpha substitution with bromine. The reaction here is actually quite simple. What you'll do is use bromine in acetic acid. So this is pure glacial acetic acid. Just has some bromine in there. It's an acid-catalyzed enolization. What you do is we will simply remove a hydrogen and put a bromine on in its place. Now, in the presence of our acetic acid, we're going to protonate our carbonyl up here at equilibrium. And that's going to give us an enol that looks something like this. Once we have the enol, we all realize that this is going to generate electron density at this carbon, isn't it? We'll get a carbanion, something like this. Again, this is at equilibrium. But once we have carbanion character at our alpha carbon, this is what we use as our nucleophile. The reaction here is simply the carbanion attacks bromine, bromine splits, we get HBr and our alpha bromo compound. Any questions? Very simple reaction, acid-catalyzed enolization. That gives us electron density here, and that is our nucleophile. Very quickly then, go ahead and write the products for these substitution reactions. Our first one here, we simply have cyclohexanone. We have bromine acetic acid. We will make an enolate on the alpha carbon, and we'll wind up with the 2-bromo cyclohexanone.
So the steps before that was with the hydrogen attached to the oxygen
Yep.
and all that good stuff.
If we want to chlorinate, we can use chlorine, usually an aqueous acid. This works fairly nicely. Again, we are going to chlorinate at the alpha position, so that's here, at the benzylic position. If we take methyl cyclopentanone and we do our bromination, we can form an enolate at this carbon or at this carbon. In fact, the product that you get is going to be this one, the 2-bromo 2-methyl cyclopentanone. Now, the reason for this is something that you already know. If you think back to reactions generating alkenes, yeah.
Sorry, you said the options were at which carbon or which carbon?
Oh, well, there are 2 alpha carbons on
Okay.
here and here.
Okay.
So, how do you know this is going to be our product? Think way, way back to when we were doing elimination reactions. We have 2 possible enols that we could write, one for each alpha carbon, right? Remember Syseff's rule? Sure you do. Syseff had a rule. Syseff simply said that when you do an elimination to form an alkene, you are going to form the most highly substituted alkene. This is more highly substituted than this guy. Therefore, this is the preferred pathway. This is the product you get. and this one is not observed. Sidesteps rule, most highly substituted alkene. Any questions? All right, we've done chlorine and we've done bromine. You can also do this with iodine. Iodine reaction is fairly special, however. If you take specifically a methyl ketone, all right, now a methyl ketone simply means we have a methyl group attached on one side of our carbonyl. So let's take a methyl ketone. Let's take aqueous hydroxide and let's add iodine. What you do is you would form the enolate anion. Enolate anion will basically have charge at the alpha carbon. So here's our anion, that's our nucleophile. This is then going to react with the iodine that we toss in there to make the iodo ketone. Now that's not surprising, that's the same thing we did with bromine, right? Well, in the presence of base, after we add the first one, turns out that adding the second one here is even easier. So this stuff is now going to react with the second mole. Going to do this to make the diiodo. Turns out that this is even a stronger acid. Therefore, this is going to react with a third mole to make the triiodo ketone. Now, we obviously can't do any more substitution. We put all three, changed off all three hydrogens, made them iodines. Still in the presence of base, however, this guy will undergo an acyl transfer reaction. Now remember that from chapter 21, right? An acyl transfer. We're going to take our carbonyl here. Here's our nucleophile. This is going to add, our leaving group here is going to be the triiodomethane anion. However, the iodines are electronegative enough that this is stable, picks up a hydrogen instantly from the water, and gives us this stuff. This is iodoform. Iodoform is a bright yellow solid. This is a standard test. Remember we talked about the Tollens test and the beautiful mirror and stuff like that for aldehydes. This is a standard qualitative test for a methyl ketone. All you do is take your compound that you think is a methyl ketone, add a little bit of base, add some iodine. If you get this big precipitate of iodoform, you've got a methyl ketone. Very standard test. Any questions?
What do you use that for?
What do you use it for? If you have an unknown compound in lab and you want to know what it is. I mean, you do a bunch of tests. You could do the Tollens test, see if it's an aldehyde. Do iodoform test, see if it's a methyl ketone, et cetera, et cetera. There's a huge flow chart, an entire science. We're doing simple tests like this to figure out what kind of compound you have. It's actually a wonderful course. But remember back in chapter 20, we wanted to make alpha-bromocarboxylic acids. Well, it turns out that you can't do the acetic acid bromine method for carboxylic acids. It just is not acidic enough at this carbon. But remember back in chapter 20, we talked about the Hell-Volhard-Zelinsky reaction, which does the same thing. Let's just review that by looking at this reaction. And very quickly, look at the conditions. Step 1, bromine, PBr3. Step 2, 2-propanol and predict the product. This was actually our first introduction to enolates as nucleophiles with halogens, again back in chapter 20. In chapter 20, we said that carboxylic acids in the presence of PBr3 were going to form acid bromides, right? Standard carboxylic acid reaction. So step 1 here, we form the acid bromide. Now the acid bromide, now that we've hit chapters 22 and 3, we realize that the bromine being electronegative is going to stabilize an anion here. Therefore, this is going to have enolate anion character, isn't it? This is our enolate anion then. Now, just like we saw with simple ketones, an enolate anion in the presence of bromine, the enolate is going to collapse, electron density here, and we would make the alpha-bromo acid bromide. Now, once again, think to chapter 21. In chapter 21, we did acyl transfer, didn't we? Here we have an acid bromide and an alcohol. Alcohol will attack the carbonyl. The strongest acid is going to be the halogen, that's HBr, versus 2-propanol. So this is going to be our leaving group, and we would make the alpha-bromo ester. So chapter 20, chapter 21, and here we are in 22. Any questions?
It's okay. I was just watching the video.
Now, as we said earlier, once we make the alpha-halo compound, this is actually nicely set up for a very simple E2 elimination. If we simply take our alpha-halo aldehyde in this case and toss in a base, what we're going to do is a simple E2 elimination. In an E2 elimination, the base is going to pull off a proton. Halogen is going to be our leaving group. So it looks like this. And we go to our alpha-beta unsaturated carbonyl. The driving force for this, remember, our alpha-beta unsaturated carbonyl is resonance stabilized, isn't it? And because of that, it's a nice stable thing. You're going energetically way downhill. Nice simple E2 elimination reaction. Any questions? The base that we usually use here is something disgusting like pyridine. We haven't used pyridine in lab because it does have a definite odor. It's a very nice organic base, however. It's a aromatic, so a 6-membered ring with a nitrogen in the ring, analogous to benzene. Nitrogen is the base. Go ahead and predict the products for these two elimination reactions. Now in our first one here, we have 2 beta hydrogens, don't we? We can choose which one is going to be eliminated. We could move a hydrogen from the methyl group and form an exocyclic double bond, or we could pull a hydrogen off here and form a double bond within the ring. Think about our Site-Ceph rule. Remember, comes back to haunt you.
Most highly substituted.
Most highly substituted. So if we do exocyclic, this is a terminal alkene. If we do endocyclic, this is much more highly substituted. Our next one is trivial. There's only one hydrogen, or actually 2 hydrogens, that are available to be pulled off. It'll be a simple elimination to give the cyclohexene. Any questions? Now, we can do this type of chemistry on basically anything with a carbonyl or a nitrile. Remember we said nitrile were carboxylic acid derivatives too. However, most esters, nitriles, and stuff like that are not going to be acidic enough to form enough of an enolate in just the presence of a dilute base or acid. Therefore, we have to cheat a little bit. The way we do this is to use a very, very strong base. One that's very popular here is lithium diisopropyl amide. This is a nitrogen anion. Now, a nitrogen anion has a pKa typically in the mid-30s. So it's a very, very strong base. Most alpha hydrogens and carbonyls are going to be somewhere between 19 and say 25. Therefore, this is a very strong base. It will yank off the appropriate hydrogen here, and it will form the enolate anion. Now there's a very cute reaction that you can do. If you want to make the alpha-beta unsaturated carbonyl, and you're dealing with an ester or a nitrile especially. And that is to dump in LDA, like we did here, make the anion. Then you add this stuff, benzene selanyl bromide. You think this sulfur compound stink, you should see selenium compounds. Once again, this is not one we're going to do in lab, because it really can be bad. But it has this very interesting property of reacting with enolates. We lose our bromine, and we form the selenium ether. If you think about your periodic table, start off with oxygen. Oxygen makes ethers, right? Change it to sulfur, going straight down the list here. Sulfur, bioethers. Well, this is the same thing. This is selenium. You could even do tellurium if you were crazy. But we can do selenium. Now, the neat thing about the selenium ether is that it's unstable to oxidation. So if we simply take this and dump in a mild oxidizing agent, something like peroxide, we put a couple oxygens on here, makes it a superleaving group, falls off instantly to give the unsaturated carbonyl. This is a very nice way to do with esters and nitriles, where the other method just doesn't work. Any questions? So let's go ahead and do a quick set. Ester, nitrile, ketone, LDA, benzene selanyl bromide, and peroxide. Go ahead and write your products.
Dr. Owens, do I have to make an organic recipe book?
Organic chemistry is simple as long as you never ever forget anything that you learned in the first semester.
We learned something in the first semester.
Our enolate anion here is going to be right here at the ring junction, isn't it? That means the selenium is going to be bonded to this carbon. When we do the oxidation, we will pull off one of these beta hydrogens, either one, and we will form the alpha-beta unsaturated ester. Once again, with esters, you cannot use simple bromination followed by elimination. It's just not acidic enough. You have to cheat and use a very strong base. Same thing with nitriles. With a nitrile, the alpha carbon is going to be acidic, not very, but it will be acidic. LDA will make an anion at the alpha carbon, so right here. That will attack the selenium. Oxidation, we will get elimination across here to form the unsaturated nitrile. And finally, LDA, this, that. We're going to form an enolate here, again remembering Sitesef's rule. This carbon will attack the selenium. We will oxidize the selenium and make the alpha-beta unsaturated ketone. Any questions? All right, so far we've made enolates, and we've used these to attack halogen and now selenium. One of the most useful things you can do with an enolate is to use it as a nucleophile against an alkyl halide. Now the alkyl halide you use here has to be simple. We're going to do an SN2 reaction. Now remember SN2 reactions. Remember back in organic 1, for an SN2 reaction, you need a nice, clean, unhindered alkyl halide. Primary works best. Benzyl, aldol, those are the super best. All we're going to do is take our alpha hydrogen here, yank it off to make an enol. Now we can do this either with acid or base. Once we have the enol, we know that that's going to give us carbanion character here. Our carbanion is now simply going to be our nucleophile attacking the methyl in an SN2 reaction to give us this substituted, alkyl substituted ketone here at the alpha position.
When you have it in like the parentheses, does that mean that that's just like the intermediate?
Yeah, this is intermediate, these are resonance forms.
Okay.
So, this is all the same thing. To say that one resonance form is the actual nucleophile is of course wrong. A resonance hybrid is a nucleophile. So that's why I grouped it all together like that. All right. Well, just like we she didn't use LDA. With our selenium, you can do the same thing here. If we simply take something with a nice alpha hydrogen, in the presence of LDA, we can make the anion. Once again, this can attack an alkyl halide. Again, we're using this resonance form as our nucleophile. And all we do is stick the alkyl group here at the alpha carbon. This works with enolates that are not as cooperative as aldehydes and ketones, and we'll see examples of this in just a little bit. Any questions?
Yes. I'm sorry, Dr. Young.
Mm-hmm.
Pardon me. But what initiates the equilibrium thing?
Well, LDA will convert it virtually 100% to the enolate anion, and it stops there.
Is it possible you could, not for this one, but the other one?
For the other one's in equilibrium, sure.
Yeah, what causes,
Oh, well,
The H
I
to
didn't
the-
include an acid or base catalyst.
oh, okay.
Because I have a proton here, I would assume that this would be acid catalyzed, but either acid or base works. Problem with having a base is the base can be a nucleophile for the alkyl halide, and you don't want that.
You have acid. it
Yeah,
attaches-
so
well, it
this should be,
attaches-
maybe an acetic acid or something like
So
that.
it attaches to the oxygen, and then hydrogen leaves from the methyl group.
Right, that's how you form the enolate. Pull off this hydrogen, put hydrogen here, so this is a tautomer. A tautomer is different than a resonance form because we're actually moving hydrogen, but the formula is the same. So it's not a resonance form, it's a tautomerization, it's called.
Yeah, that's what we was talking about.
That's a lot from last semester.
All right. Look at these guys. These are all treated with LDA, THF as a solvent, a tetrahydrofuran, and then we're dumping in bromomethane. In our first one, we have a carboxylate ester. We know that those are not acidic enough alpha hydrogens just to do this stuff by themselves. Therefore, you have to add LDA to make the enol. The enolate anion will be here at the alpha carbon. That will then attack bromomethane. And all we've done is stick a methyl group here now on the alpha carbon. Same thing with the nitrile. We can't form much of an enolate population without using something like LDA. The enolate anion will be here at the alpha carbon. That will then attack the bromomethane. And all we've done is put a methyl group here on our alpha carbon. Finally, down here we have methyl cyclohexanone. We would expect the enolate anion to form here. We would expect this then to be our nucleophile. However, with this particular compound, if we tried to form an enolate here and then use this as a nucleophile, it's just way too crowded. So the product is actually this stuff. Again, trying to put a methyl group here is just unfavorable.
It's very scientific.
So
It's
this
crowded.
is, yeah, Yeah, nobody likes a crowd. So that's one of the rules for organic chemistry, I guess. So side-step rule usually works. However, in this case, once you form this enolate anion, it is uncrowded enough that it reacts faster to give this product. Yeah.
Okay, so I might be the only one who's just a little confused. So last time it was that we make it unsaturated, and this time we're keeping it saturated. And I don't know, like, when you know which one it is. Does it?
Well, okay, so what happens when you dump in LDA here? Go back to, just for your general mechanism. When you dump in LDA, you're going to make an enolate anion, right?
Right.
That's our double bond. Enolate anion is going to have either a double bond here, with this being O minus, or it's going to have a double bond here. Now, SciSap would tell us that the double bond here is more highly substituted and will be favored. And he's right. However, in this particular case, even though this is the favored enolate anion, this is so crowded that using it as a nucleophile is just very ineffective. So even though you've got just a little bit of this stuff, the anion on this side, because it's unfavorable, every time you form it, it reacts to give you the wrong product.
What about on the last one? Because, I mean, that one also, you just stuck a methyl group. You didn't do a double bond.
But this guy here,
Right.
no, same thing. We have a double bond here. The negative charge is on the nitrogen. We didn't actually draw that one out, but that's how a nitrile delocalizes the negative charge. Maybe I have a picture of that later.
Okay, so that was the intermediate step.
Yeah.
How do you spell this guy's name? Sidestep?
SciStep. SYCZEF or something like that. Type it into Google, it will correct it. All right. So let's do our bottom line here. I put in these bottom line slides to help you remember or to answer the question, what do I have to know? Well, we're going to have 5 of these things. Make sure you know them. Okay? If we have an enolate like this that we form with something like LDA, or for aldehydes and ketones, just with acid or base, we can react these with an alkyl halide. All we're doing is introducing an alkyl group on the alpha carbon. Aldehydes and ketones, we can form the enolate just with acid or base. But with esters and nitriles, we need something bigger. LDA works nicely. Get the enolate here, tack RX. Here's our compound we started with. All we do is stick on the alkyl group. All right, let's look at an example of that. Tell me how you get from here to here. We're starting with acetaldehyde. We're going to butanal. All right, ask yourself the magic question. What have we done here? What type of molecule is it? Well, it's still an aldehyde. We just stuck a couple extra carbons on. Where did we stick them on? We added them to the alpha carbon. So these guys, these carbons, are from acetaldehyde, aren't they? And these two carbons we've added. All right, how many ways do you know to add carbons to the alpha carbon of an aldehyde? The only way you know is to make an enolate anion and react it with an alkyl halide. Enolate anion would look like this. This is the enolate anion of acetaldehyde. Right? Acetaldehyde, here's this enolate anion. Our alkyl halide, that's the other two carbons. These guys. That is simply bromoethane. The reaction, the enolate anion attacks, bromine leaves, and that gives us our butanal. Finally, how do we make our enolate anion? Well, because it's an aldehyde, we can either use LDA, that would work, or we could use just plain base. Base is simpler. LDA works fine. Conditions LDA, THF, bromoethane, or just hydroxide followed by bromoethane. Either one would work. We'll see that there's a problem with hydroxide in just a minute. This is a little cleaner. All right, everybody happy with this? Let's see some happy faces. All right, everybody's happy with this. Okay. Do this one. Once again, we're starting with acetaldehyde, that's ethanol. And we're going to 3-hydroxybutanol. Now, you know, this should seem like deja vu all over again, right?
Yes.
The two carbons of our acetaldehyde are going to be these two. So the bond we made was that. Everyone happy with that?
Okay.
Now, last time, what did we do? We asked the question, what enolate and what was our electrophile? The other one we used, bromoethane is the electrophile, right? So our enolate is going to be the same thing here, right? Just get this from that. The alpha carbon is going to attack to give us this hydroxy group. Now think. You can do this. What did this carbanion attack to give us this? Here's the bond we made. So what was attached to this half? It was two carbons, hydrogen that we don't show, and an oxygen, right? So what was it? It was acetaldehyde. And all in the world that happened was the enolate collapses. This becomes an OH. And here's the bond we just made. So how do you make this enolate? Well, here we don't want to use something like LDA because we need acetaldehyde to be our electrophile, right? So here we're just going to dump in hydroxide. This, my friends, is what we refer to as the Aldol condensation. The trivial name for this molecule here is aldol. You make it by taking 2 moles of acetaldehyde, treating it with base, and that's what you get.
Which one is
Aldol condensation, very, very important reaction in organic chemistry and in biochemistry. Yeah,
Which one did you say was aldo?
this general reaction, 2 moles of aldehyde or ketone, works for ketones too, in the presence of base, gives a beta hydroxy carbonyl. Beta hydroxy carbonyl. Now this is the only one that is truly aldol condensation because this is aldol. When we do these types of reactions, we refer to them, I suppose, correctly as aldol type. However, most people would just call it an aldol. For example, if we take 2 moles of this stuff and we treat it with base, what are we going to make? If you think about it stepwise, you can't go wrong. What's the first step going to be? We're going to make the enolate anion, aren't we? So it's going to be at this carbon. Draw the structure of that enolate. All we're doing is pulling hydrogen off here, making SO minus. We know that that's going to react with another mole of our aldehyde, so that's what this is. And this is the enolate anion. Pull off the alpha hydrogen, make the enolate anion. Now, go ahead and collapse your enolate, do your attack, and draw the structure of the beta hydroxy aldehyde. You're going to form a bond between the alpha carbon and the carbonyl. Carbonyl is going to be the OH group. And it should look like this. Now, when you look at a spider like this up on the board, it's difficult sometimes to figure out what you've done, but the bond you just made is this one right here. The alpha carbon, that's this guy, attack the carbonyl to make the OH group. Here's our carbonyl. This is the alpha carbon. That's the beta. So it's a beta hydroxy aldehyde. Let's do that again. If we simply take cyclohexanone and we stew it up with base, what are we going to get? You're going to need a cyclohexanone for your electrophile. And you need the enolate anion. All the structure of your enolate anion. The pair should look like this. Here's our electrophile, and there's our enolate. Now this enolate is going to collapse, and when it does, the alpha carbon is going to attack this carbonyl. Draw the structure of our carbon. We are going to have a bond between our alpha carbon and this carbon that used to be the carbonyl. This guy will be an OH, and it will simply look like that. Once again, the bond we just made is this one right here. Any questions? Now remember how I said that an aldol condensation was a very important reaction in organic chemistry, and I used the B word, I said biochemistry, right? Ever heard of the enzyme aldolase? Aldolase is one of the key enzymes in glycolysis. Glycolysis is what makes everything run, including your brain. Aldolase will take dihydroxyacetone phosphate and glyceraldehyde phosphate and perform an aldol condensation. This is dihydroxyacetone. Acetone in the middle, two hydroxy groups. Dihydroxyacetone phosphate. We simply stick a phosphate on one of them. Glyceraldehyde. Glyceraldehyde is a 3-carbon aldehyde. We put a phosphate down here. So those are the players. Now, dihydroxyacetone phosphate binds to the enzyme. When it does, the carbonyl reacts with a lysine. The lysine has a primary amine on its side chain, and it forms an imine, a carbon-nitrogen double bond. So, we have this. The imine, this guy right here, just like a carbonyl, except we can protonate it easily, really acidifies the alpha carbon, doesn't it? Now the enzyme is set up so that it has a histidine, which is a base, in such a position where it can yank a hydrogen off. When it does, it forms this guy. Now this is actually an enamine. Remember those? But we can also just think of it as a simple enol. Now, being a simple enol, that means that here at the alpha carbon, where we pull the hydrogen off, we're going to have a partial negative charge. In comes glyceraldehyde phosphate. This has the carbonyl that we're going to add to. All that's going to happen is that our alpha carbon is going to attack the carbonyl, and we will form this stuff. Now, as we look at this, we say, oh my gosh, how did that happen? The bond that we just made is this one right here. In between these two carbons, this was our alpha carbon, that's this guy. This was the carbon from acetaldehyde. Now, this is bonded to the enzyme still as a shift base, it's called. It's an imine. The next step is to hydrolyze that back to the ketone. When we hydrolyze it back to the ketone, the enzyme lets go of it. And now finally, to complete our course in organic biochemistry, we have a ketone. And what's here? It's an alcohol. The oxygen is 5 centers away from this, isn't it? What do alcohols and ketones form? Ketones. This forms a hemiketal that rejoices in the name fructose 1,6-bisphosphate. Aldol condensation in reverse is glycolysis. Start off with glucose, work your way down to fructose 1,6-bisphosphate, do the reverse aldol condensation, you're left with dihydroxyacetone and glyceraldehyde phosphate. That is the organic chemistry of glycolysis. Isn't that neat? Really is neat. All right, as we said a while ago, whenever you have substitution, either alpha or beta, and that happens to be a leaving group, we can do a simple elimination to form again our unsaturated carbonyl. Hydroxyl group can be a decent leaving group in the presence of acid. Simply protonate it. This leads, again, an E2 elimination to give the dehydrated product. Dehydration of a beta hydroxycarbonyl actually occurs very, very easily. It's almost impossible to not have it happen. Go ahead and just take these and convert them to the alpha-beta unsaturated carbonyls. You see, the early biochemists were actually organic chemists. That's how in the world they managed to figure out things like glycolysis, because they knew that. Oh, that's just a reverse Aldol condensation. There's also a very important enzyme in metabolism called enolase. And what does it do? Catalyzes the formation of enolate anions. All right, we're going to eliminate water. It's going to be alpha-beta unsaturated, so our double bond is here. And that's our ketone. The next one, going to eliminate the hydroxyl group, proton from here. There's our alpha-beta unsaturated aldehyde. And finally, after we condense 2 moles of cyclohexanone, we had this. When we eliminate, we're going to pull off the alpha hydrogen, form a double bond between the 2 rings, and it will look like that.
So So okay if mine looks different?
As long as there's the same amount of carbons.
Nope, same thing. Just make a double bond here between the alpha and the beta carbons. So let's take our concept of our aldol synthesis and include the dehydration step. If I ask you to make this guy using an aldol, how would you do it? All right, you would look and say, what is it? It's an alpha-beta unsaturated aldehyde, right?
Yes.
How do I know to make those from an aldol? Well, an aldol is going to give us a beta-hydroxyaldehyde, isn't it? So step one, ask yourself, where was the hydroxyl group? That was attached here at the end of the double bond. So simply draw the beta-hydroxyaldehyde. Yeah.
When we use the word aldol, are we talking about the specific aldol or aldol?
Aldol type condensation.
Okay, cool.
Again, it's, the general term.
So, okay.
So it's going to be base catalyzed condensation of
It's
2
gonna
moles of
look like it,
ketone.
but it's gonna be like a ethyl instead. No.
Well, do it stepwise.
1, 2, 3.
We used to have a hydroxyl group here. So our beta hydroxyaldehyde looked like what? It was simply that. We had a hydroxyl group in the beta position. All right, now you look at it and say, this is a beta hydroxyaldehyde. We made that by an aldol condensation, didn't we? So 1 mole of something made the enolate, and 1 mole, the second mole, was the electrophile. This is the bond we made. So half of it is simply 1, 2, 3, 4 carbons. That's butanol, isn't it? And the other half is our alpha carbon. That was the nucleophile. And again, it's 1, 2, 3, 4 carbons. So it's the enolate of butanol. The enolate and aldehyde look like this. This is our butanol, that's this half. This is the enolate, that's this half. And so the conditions you would show, 2 moles of butanol, presence of base, we get this. Step 2, dump in acid, and we dehydrate.
Nicely done.
Thank you.
Way to bring it together. Is that everything? We got more.
Oh, can you go back for a second?
All right, let's just play with this a little bit. What if I take this 1, 2, 3, 4, 5, 6 hexane dione, and I throw it into base. And I'm going to let it do an aldol, then I'm going to dump in acid and let it dehydrate. What's our product going to be? Think about it for a second. Now there are 2 things you should be thinking about. One is, we could take one of these, make an enolate, attack another one. By gosh, that could then attack another one. That could then attack another one. Kind of like we did with nylon. Except in a case like this, you wind up with something that's called tar. And you don't want that. Yuck. The product actually looks like this. Now let's think about how in the world that happened instead of making tar. This guy is going to form an enolate. Let's make an enolate. Now, in order for this to form a cyclic product, what we're going to have to do is take this enolate, this end, and use it as our nucleophile against this carbonyl. This is probably easier to see if we take this and just change its conformation a little bit. All I've done is rotate here so that this is now closer to my carbonyl. Now, when this enolate collapses, the anion can attack the carbonyl that's here 5 centers away. So what we have is this. Enolate collapses. We attack our carbonyl and make our alcohol.
How do you know the double bond was going to be on the very end?
It's actually in both places. It's all places, isn't it? But if it was here, we would form a 1, 2, 3 carbon ring, and that doesn't work very well. So the 5 carbon ring is so much more favorable thermodynamically. Once we're at this point, all we do is dehydrate it with a little bit of acid to make our alpha-beta unsaturated ketone. Now, this is called, why doesn't this give tar? Okay, why? Because we can form this 5-membered ring. It's an entropy-driven effect. If it's 5 centers away, it's close enough that it's about 1,000,000 times more favorable than 2 molecules bumping into each other. So you get 1,000,000 to 1 preference for the entropy-driven reaction, also called the Cersei effect. Again, this is how another way that enzymes catalyze reactions. They take the appropriate groups, put them in the right spot, boom, you get reaction. All right, our second point to remember. If we make an enolate of aldehydes or ketones, these can undergo Aldol type condensations to give beta hydroxy aldehydes or ketones. Second thing to remember, if you take that in the presence of acid, it dehydrates to give alpha-beta unsaturated aldehydes and ketones. So far, only 2 things to remember. Plus all of 234. Let's just diverge here for a second. Remember I said that making an alpha-beta unsaturated compound was good because we can do things to it. We covered this back in chapter 19, I believe. We did simple Michael additions. Remember the Michael reaction, you add a nucleophile to the beta carbon. Reason this works. Remember, this is what our carbonyl compound, these are its resonance forms. we have partial positive on the carbonyl carbon, and here at the beta position. Again, we did this back in chapter 19. Because we have partial positive character here, this can react with a nucleophile, and we wind up with beta addition. Now back in chapter 19, we looked at a few reactions. Let's just see if we remember them. Cyanide, or perhaps best, diethyl aluminum cyanide, undergoes Michael reaction with alpha-beta unsaturated carbonyls to give what? The cyanide simply adds to the beta carbon to give the nitrile. We also said we could take an alpha-beta unsaturated carbonyl and react it with dialkyl copper lithium. Same concept here. The anionic nucleophile, the methyl group here, simply adds beta to give us that. And finally, we said we could do the Michael reaction with amines. Nitrogen is going to attack the beta carbon, and we get the amine. Now this is stuff we already know. Predict for me the product of the pentane dione enolate anion with an alpha-beta unsaturated ketone. Draw me a product. Pentane dione anion will have an ionic character here, won't it? The middle alpha carbon. This is our nucleophile. It's simply going to add, just like everything else did, and we reform that. Bond we just made is this thing, just like we made these bonds up here.
Did you just kind of turn it?
Bottom line is, if you take an enolate anion, you can react that with an alpha-beta unsaturated ketone or aldehyde and do simple Michael addition. No different than cyanide, dialkyl lithium, or amines. Again, here's the bond we just made. All right, quickly then. Draw these bizarre looking products. All you're doing is adding the alpha carbon to the alpha-beta unsaturated carbonyl. If you think about it, this guy looks a lot pentane dione-like, doesn't it? Going to form a nice anion right here in the middle. It will attack the beta carbon, and you would form that. Again, the bond we're making is simply this one. we could take, this is called malonitrile. Even though it's a nitrile, we can form a fairly decent anion at the central carbon. It will just add to our beta carbon, and we will get that. And finally, this stuff. We'll learn to appreciate this. This is called methyl acetoacetate. Anion right here. Add to the beta carbon to give us this. Now these reactions with compounds that have way too many carbonyls got to get us into something that is called the Malonic ester synthesis. This diester up here, this is dimethyl malonate. Malonic acid is 3-carbon acid, CH2 in the middle. And as you can see, this is going to form a nice stable anion, isn't it? In the malonic ester synthesis, we're going to take a malonic ester in the presence of base. Now, the base that we use for this, you match the alcohol with the alcohol that's in your ester. You do that because they exchange, and it makes it messy if you don't. So here we have diethyl malonate, and we have ethoxide as our base. Not surprisingly, we pull off the alpha hydrogen. This is our anion. Everyone happy with that? All right. Again, there are too many carbonyls, and that makes everyone nervous, but so far we're all together here, right? Now, what have we done with enolate anions? We've reacted them with electrophiles, right? So if I took this and simply stuck it in the presence of an alkyl halide, it wouldn't be at all surprising that I could alkylate it, correct? Just like we've done with lots of enolates so far. And what does this give us? Well, it gives us a diethyl malonate with this alkyl group sticking here. So that could be a methyl, ethyl, propyl, benzyl, whatever. Oh, that's kind of neat. Anyone have any problems so far? Enolate, alkyl halide, simply alkylate the alpha carbon. Now is when it gets fun. Because I'm going to take my substituted diethyl malonate and I'm going to dump it into acid. What happens to esters when you dump them into acid? They hydrolyze, don't they? They hydrolyze to the carboxylic acid. Okay? So what we have now is a substituted malonic acid. Now think back to chapter 20. Ever heard the word decarboxylation? Yes, you did, in chapter 20. We said that if we had a beta diacid in the presence of acid, that this would undergo a magic cyclic reaction where we would lose CO2. The magic looks like this. we wind up with an enol and CO2. What we've done is simply to take one of these carboxylate groups, convert this to CO2, and we're left with the other one. And it fizzes. Chapter 20. Now, we have an enolate here, don't we? That's not going to stick around, not happy. It's going to convert back to the carbonyl. When it comes back to a carbonyl, what's it going to form? These electrons move in, they move out, and we get a substituted acetic acid. The Malonic ester synthesis gives us a way to make substituted acetic acids. The R group we stuck on here could be anything. So if you look at a synthesis and you say, okay, this is a substituted acetic acid, what you should say is, I can make that from malonic ester. Let's do that. How would you make this from a malonic ester synthesis? Well, you want to look at it and say, these two carbons would be an acetic acid, wouldn't they? This is the bond we made in the malonic ester synthesis. So, one reactant is going to be a malonic ester. Diethylmalonate, that works fine. All you have to do is figure out what the second reactant was. If this is the bond that we made, then the alkyl group that we introduced had 1, 2, 3 carbons with a double bond out here. So the malonic ester that we had to look like this. This is malonic ester with 1, 2, 3 carbons and a double bond attached here. So what was our alkyl halide? The alkyl halide had 1, 2, 3 carbons, and here was the halogen. One, 2, 3 carbons, halogen attached here. And we're simply going to react this with diethylmalonate to complete the synthesis. Now this is real organic chemistry. We finally arrived. This is what we worked 2 semesters to do. Let's do this again. Oh my goodness, we're making a ring. But even though we're making a ring, this is still a substituted acetic acid, isn't it? These 2 carbons are our acetic acid. the bonds that we made were this one and this one. This is what our ester looked like before we decarboxylated. And again, the bonds we made were here and here. There's our carboxylic acid, and this is the stuff that we added. Now, what was the structure of our compound? What you have to do is simply break the bonds that you just made. The alkyl halide had 1, 2, 3, 4 carbons, and let's say it had a bromine on each end. So the alkyl halide would have looked something like that. And these are the bonds that we just made. We take 1, 2, 3, 4, 1 for dibromobutane, malonic ester, make the cyclic adduct, decarboxylate, and we're here. Now the next 3 things are like test questions, okay? So let's think about this. If we were going to make this using malonic ester in a little space that'll be over here, draw the structure of the alkyl halide that you need. You want to look at it and say, okay, what came from where? Here's our acetic acid. This is the alkyl halide. This part came from our malonic ester. This part, in red, came from the alkyl halide. All you have to do is take your malonic ester and now draw me the structure of your alkyl halide. This stuff in red was simply bonded here to an alpha carbon, and this alpha-methyl benzobromide would be our electrophile.
Yes.
So on the exam, you would get this, and of course you would enter this structure. Do it again. How would you make this? What the alkyl halide? Which carbons came from malonic ester? Which came from the alkyl halide? Malonic ester gave us the 2 carbons of the acetic acid. And the 2 methyl groups here are from the alkyl halide. Go ahead and draw the structure of the alkyl halide. This one is so simple. We're simply doing it twice. We need 2 moles of bromomethane. Do it again. The acetic acid portion is these two carbons. The other part came from the alkyl halide. Draw the structure of the alkyl halide. It had two benzene rings, a CH, a CH2, and a bromine. All right.
Yeah.
Now these are regular test questions, right? This one is the extra credit. But you're going to do it the same way. Identify two carbons of the acetic acid. That's going to be this and this guy, right? So these are the two bonds you made, and this is from your alkyl halide. The alkyl halide must have had a 5-membered ring, 1, 2, 3, 4, 5, right? CH2Br, CH2Br, and would look like that. Now, if you would have gotten this and drawn it flat, I still would have been really happy with you. Okay?
Hey, is that? Okay, never mind.
That's it. 5-membered ring, CH2Br. So bottom line number 3. If we do a malonic ester synthesis, what do we make? A substituted acetic acid. That's simple. Now we have 2 more reactions to cover. These get a little more complicated, just a little. This is the acetoacetic ester synthesis. Now, ethyl acetoacetate is simply this. When we say acetoacetate, this would be the 2 carbons of an acetic acid, and here in the alpha position we have a carbonyl and a methyl. So that's all that is. Ethyl acetoacetate. Just like pentane dione, very acidic hydrogen here, right? We're all happy with that. Put this in the presence of ethoxide, and we're going to make the enolate. Everybody's happy with that. What do we do with enolates? We react these with an alkyl halide, and we wind up with the alkylated ethyl acetoacetate. Everybody's happy with that too. Now comes the magic. What's going to happen when we take this stuff and dump it into acid? Again, we're going to hydrolyze the ester, and we're going to decarboxylate. Step 1, we hydrolyze off the ester. Now this is just like we just did with malonic acid, right? Except instead of having carboxylate on both sides, here we just have a ketone. But it works exactly the same way. This is a beta-keto acid, and they decarboxylate just as easily as the others. Going to lose this as CO2, and we're left with this. Go ahead and convert this into a carbonyl compound before I push the button. It's a race. Convert the enol into a carbonyl. We can do that. We know this is going to be our carbonyl right here, right? We're going to have a hydrogen down here. What have we made? A methyl ketone. Malonic ester gave us a substituted acetic acid, right? Acidic ester gives us a substituted methyl ketone. The 3 carbons from the ethyl acetoacetate are these guys, and we've simply attached an R group. Just like before. How would we make this? Using acetoacetic ester synthesis. We would look at it and say, what is it? It's a methyl ketone, right? So where's the bond that we made? In this synthesis, we're going to keep these 3 carbons, here, here, and here. We keep those. This guy is going to go with CO2. And we're going to put something on in its place. These 3 carbons from the ethyl acetoacetate, and these 3 carbons from an alkyl halide. Here's our alkyl halide. The anion will simply attack. We'll get this. Here's the bond we made. When we dump this into acid, going to lose this as CO2, and we're left with 1, 2, 3, 4, 5, 6 carbons and a carbonyl. So this is just like the malonic ester synthesis, except different. Here we make methyl ketones. Number 4 on our list. Ethyl acetoacetate, alkylate it, decarboxylate it, so we lose the ester moiety altogether, and we make a substituted methyl ketone. Now there's only one more thing that I can fit on the slide here, so that's it, number 5. And the last thing we're going to do is called the Claisen condensation. Claisen was a German chemist, one of these guys that figured all this nonsense out. They were actually brilliant. They had no spectroscopy, they just did everything. They were very, very good. If we take something as simple as ethyl acetate, and that's simple, right? We know that these things don't form enols very well. They don't. But if we take this and we put it in the presence of ethoxide, we will still get a little tiny bit of enolate form. The enolate would look like this. Now we still got mostly this stuff, don't we? But a little tiny bit of our enolate. Now we all know what's going to happen, right? The enolate's going to collapse. Alpha-carbon's going to attack the carbonyl. We know that. When we do that, we're going to get a tetrahedral intermediate. Remember chapter 21. Our leaving group here from our tetrahedral intermediate is going to be ethoxide, isn't it? Now remember, we're swimming in an ocean of ethoxide, so that's okay. So when this collapses, it's going to kick out the ethoxide. Draw the structure of what's left. Go ahead, kick out ethoxide, collapse the tetrahedral intermediate, and give me a structure. This is going to be a carbonyl, isn't it? Right here. Going to be bonded to a methyl, then to a CH2, then to an ester. What is it? Hi, George, it's ethyl acetoacetate. How about that? That's how you make it. Simple Claisen condensation. Now, what I want you to remember, again, going back to chapter 21, this is just acyl transfer. We do an addition, get a tetrahedral intermediate, leaving group leaves to give us our carbonyl. So let's do it again. Let's take this stuff, in the presence of ethoxide, and do a Claisen condensation. Step 1, draw the structure of the enolate. In the enolate, our double bond is going to be right here between the alpha carbon and the carbonyl. This will be O-. It's a Claisen condensation, so this enolate anion is going to attack a carbonyl of another mole of ester, right? And it's going to give us a tetrahedral intermediate. This collapses, electrons move up, and our tetrahedral intermediate looks like that. Now, in our tetrahedral intermediate, ethoxide is our leaving group, right? That means that this is going to be a carbonyl, going to be bonded to a CH2 and then an isopropyl, CH, isopropyl, and ester. And it would look like that. Now Now, you know what I'm gonna do? I'm not gonna leave this stuff alone. I'm gonna take and dump it into acid. And when I do, what's gonna happen to my ester? It's gonna hydrolyze, right? And that's gonna give me a beta keto acid. This is the bond we just made. Now when I dump this into acid, we're going to hydrolyze the ester to the carboxylic acid, right? Just like we saw with malonate and with acetoester. This is going to be a beta keto acid. This part is going to come flying off as CO2 and draw the structure for me of what's left. We will have a carbonyl in the middle, won't we? On one side, we will have a CH2 isopropyl. On the other side, we will now have a CH2 at this point and an isopropyl. And it looks like that. Whenever you do a Claisen condensation and then dump it into acid, you make a symmetrical ketone. Same thing on both sides. Which now brings up point 5. Enolates of esters add to the carbonyl of a second to give beta ketoesters, dump it into acid, and you get symmetrical ketones. These are the 5 things you need to remember for these 2 chapters. So let's just wind this up quickly with 3 simple reactions. Look at our first one. What is it? It's an ester, right? And we have it in the presence of alkoxide. This is a Claisen condensation, isn't it? And then we're going to wind up dumping it into acid. We will make a beta keto ester, and then we will decarboxylate. We remember point number 5. We will get a symmetrical ketone, won't we? We know that. So let's do it. First step, enolate is going to attack an ester. Our tetrahedral intermediate will look like this. Methoxide is our leaving group. And this is our beta keto ester. The second thing we did, step 2 in our reaction, we took this and dumped it into acid. In the presence of acid, we're going to hydrolyze our ester to carboxylic acid. It's going to go away as CO2, so we're going to lose this whole chunk. And we will be left with a symmetrical ketone. So our first problem looks like that.
That was just with
Do your next one. Now this one has an interesting twist that goes back to chapter 20 as well. All right, not surprisingly, in the presence of base, we will form an enolate anion there, right? This is what it actually looks like. Remember, we're putting a negative charge out here, but there's negative character on the alpha carbon. I knew I had it in there somewhere. So that's our enolate. This is going to be our nucleophile. It's going to attack allyl bromide. So here we go. Simply going to attack. And we've made our malononitrile with our 3-carbon chunk attached. Everyone happy with that one? Now, remember in chapter 20, carboxylic acids, we had a way to make carboxylic acids from nitriles, didn't we? How did we do that? We simply dumped them into strong acid. In fact, we did that in lab. Benzonitrile to benzoic acid. You did it yourself. Remember? Of course you do. So if we take this stuff now and we dump it into acid, these are going to hydrolyze to carboxylic acids, aren't they? Both of them. And what is this? That's malonic acid. And what does malonic acid do? It blows off CO2, doesn't it? When it does, this goes, hydrogen goes here, and therefore our product, just like a malonic ester synthesis, is a substituted acetic acid. That's why this stuff is called malononitrile. Malonic acid, malononitrile. They're equivalent. Now I know nobody wants this to end, but this is our last problem. Do an aldol condensation on this compound. Our simple aldehyde is going to form an enolate, which is going to attack a second mole of aldehyde. When it does, the aldehyde carbonyl will become an OH group, and we simply make a bond between the alpha carbon of one and the carbonyl carbon of the second. And we get a beta hydroxyaldehyde. Now we didn't show a dehydration step here. We know that if we dump this into acid, we can make alpha beta unsaturated, but the answer to the problem is simply beta hydroxyaldehyde. Now, isn't this a fun set of chapters?
Yeah, definitely.
This is why organic chemists love organic chemistry. This is the fun part. Now you get to take all these tools that we've developed over 2 semesters and use them to make really fun things. We have one more chapter to do, that's amines. We'll do it sometime, I'm not sure when, but we'll do it. And then we're gonna have an exam. It'll be a take-home exam.
Thank you, Jesus.
Surprise.
Let me wake up. Wow, that's awesome, man.
It will be a take-home exam. And it will cover everything from aldehydes and ketones through amines.
One day.
That is awesome.
Then we'll come back and we'll do review for our final exam, and then we'll do that.
Do we have 2 more quizzes?
Oh yeah, we have another quiz sometime too.
This is like gonna be before the,
Means I
Before
can't
the
see.
exam, right.
When is this take home exam?
What?
I'm not sure.
It's so
Okay,
big.
so we
After
still
we
have
do
some
24.
time, right?
So it'll be after.
No, I have to
Right?
like,
Okay.
his relief is like so
All right.
evident. I don't even know how to